Imagine we have two carts, A and B, rolling toward each other. They collide, and then they move apart after. We've seen that the momentum A gains or loses is equal and opposite to the momentum that B gains or loses. This is a strange concept, but in the end it comes down to Newton's third law. A gets pushed to the left with some force, and B gets pushed to the right with an equal and opposite force. If the objects feel the same force, and it occurs for the same amount of time, because they both experience the same collision, then they have the same net impulse. And if their net impulse is the same, just opposite in direction, then delta P is the same, but opposite in direction. This has a really interesting consequence. We can take this equation on the bottom in purple, and we can add delta PB to both sides. This says that the change in both, the total change, is 0. In other words, if you have 5 Newton seconds of momentum at the beginning as your total, then you have to have 5 Newton seconds of total momentum at the end. The total change has to be 0. This has some really interesting consequences. Imagine you're on a skateboard, let's say. Here's your skateboard, it's got some wheels, and you're standing at rest like this, but you're ready to pounce. Right now, you are at rest. The skateboard is at rest. Let's assume it's a frictionless system. We can assume the system is isolated, and that means that the whole analysis where we say the forces are equal and opposite, then we multiply both sides by delta T, then we say that's equal to the net impulse, and then that has to equal the change in momentum. This whole trick only works if the force, Fa and Fb, if the collision force, is the net force. We can't get to the net impulse from the second line unless the force is the net force. So we have to assume that the collision force, Fa and Fb, is in fact the net force to have this consequence, for this to be true. So that's what we mean when we say the system is isolated. We mean that all of that logic is valid. The collision force is in fact the net force. So if the person jumps off to the right, like this, and now they're moving to the right, what does the skateboard have to do in response? Well, we know the total momentum stays the same. What is the total momentum at the beginning? It's 0, because everything is at rest. So at the end, the person's final momentum plus the skateboard's final momentum has to be 0. If the person has some positive amount of momentum, maybe it's 4 kilograms meters per second, then the skateboard must have some final negative momentum, which would exactly cancel the person's. This way, the two add together to give 0. The initial momentum and the final momentum are the same in total. Let's see another example. There's a person skating along the ice. And they're holding, it doesn't look like a person. They're holding a big bowling ball over their head. There's their scarf, cape, and this is a bowling ball. It's heavy. They're going to take this bowling ball and throw it to the right. There it is, it's moving to the right. So initially, both objects are at rest. What's the total momentum of both objects at the beginning? It's 0. Momentum is mass times velocity. The person's velocity is 0, and the bowling ball's velocity is 0. At the end, what's the total momentum? Well, it has to be the same, 0, because we can assume the system is isolated, or it should be said, the system is isolated, let's say. That means that the final total momentum and the initial total momentum have to be the same. How can we possibly get 0 momentum on the whole from this system? Well, if the object, the bowling ball, has some positive value, then the person must have some negative value that's equal but opposite. That means the person has to be moving the other way, to the left. Now, they do have the same momentum change. Delta P is the same for both. J net is also the same for both, because they feel the same force for the same time. Even the force is the same for both. But what about their acceleration? What about how much they speed up? Well, if we take the equation F net equals ma, and we divide both sides by mass, mass cancels out, and we have acceleration equals net force over mass. If they feel the same net force, then both objects, the person and the bowling ball, they have the same numerator. But the person has a bigger mass. So if you divide the same number by a bigger denominator, you get a smaller acceleration. The person has less acceleration, and they speed up less because they have a bigger mass than the bowling ball.